we've lowered the peak temperatures of the cycle, what happens to the rest of the temperatures of the cycle? They're all lower, so the exhaust gas temperature is going down as we begin to really add a lot of residuals. Okay? You see what's happening up at the top, you see what's happening in the bottom. In the middle there, we've had to increase the intake manifold pressure a bit to get the air into the cylinder and to overcome what is a drop in efficiency. We need a little more fuel and air in the cylinder. And also the pressure is higher in the cylinder because it now contains more residuals. So we have to increase the intake manifold pressure a bit, which means we reduce the intake manifold vacuum, right? The vacuum is this is the vacuum, the difference in between atmospheric pressure and the manifold pressure. And if this is 0 down here, this is manifold pressure, is the absolute manifold pressure. And the vacuum is this distance. So as we decrease the vacuum, what happens to the manifold pressure? It goes up, and we have more gases in the cylinder. Those gases are comprised of a little more fuel and air because we've hurt the efficiency by burning it more slowly. Why does burning it slowly hurt the efficiency? What happens to the cycle when we burn slowly?
It just gets compressed.
We have to start earlier, we come like this, and we've got an increase in time losses, right? And what we're holding constant here is the IMEP, indicated mean effective pressure, which is the average height of the work loop. And they're holding that at 50, if I remember right. Yeah, 50 PSI. That would be the average pressure, which if we push down on the piston with a constant pressure, we get the same amount of work as in the work loop. Okay. And so we can see in the middle there, we can see a steady increase in the amount of residual fraction as we open the intake valve earlier. But then when we open the intake valve later, unlike the exhaust, what happens? We open the intake valve late, if you look at the figure, what occurs?
Less residuals?
There's less residuals.
Yeah.
And eventually we reach a point to where opening it much later really doesn't change things much. We've gotten down to almost no residuals at all. Certainly half of what we had originally. Why would very late, you can look at the bar graph and see what they mean by very late at the top. The crosshatch sections of the bar graph shows what is the variety of timings that they've chosen. So when it's open very, very late, what's happened?
The intake valve closes late?
It's opening over here
There's like less blowback.
after the exhaust valve is closed.
There's no blowback, right?
And yeah, once the exhaust valve closes, that determines the amount of residuals. They may be still some of them in the intake manifold, but they're not going to change after the exhaust valve closes because the only place to get residuals is from the exhaust. So we would expect it to get very, very flat as we open the intake valve very late, and that's what we see here. Now, as we open the intake valve later and later, the exhaust valve temperature is dropping, even though we're in a range where the residuals are relatively constant. They're decreasing, but they're not decreasing much. Why is the exhaust gas temperature dropping? As we decrease the residuals, we see we can steadily reduce the spark advance, which means what's happening to their flame speed?
Speeding up.
We're burning the mixture more rapidly. We now are reducing some of these time losses.
just getting more efficient, right?
Yep, more efficient. What's happened to the effective expansion ratio? As I reduce the time losses, what's happening to the effective expansion
It goes
ratio?
up, right? Goes up.
It's getting bigger. And so what we would expect to see is a drop in exhaust gas temperatures. Okay? It also, we get to a point where we open the intake valve late, where the duration of the intake stroke has been impacted so much that we have to go to a noticeably lower pressure to get the gases into the cylinder. Okay? Is that
Well,
clear?
because it's getting more efficient. Pretty much. Because you have less exhaust.
Are there any questions, John? See, those are the two events that determine valve overlap. When the intake valve opens and when the exhaust valve closes. And as we try to deliver more power from the engine, we need to open the intake valve earlier and close the exhaust valve later to allow a greater amount of time for the gases to pass through the engine during the intake stroke and the exhaust. So we're going to have some valve overlap no matter what the situation. And as we try to build an engine with higher and higher output per displacement, we're going to have more and more valve overlap. Variable valve timing can help that to a certain degree, but if you're moving the entire cam, at the same time you're affecting these two events, you're affecting the exhaust valve opening over here and the intake valve closing over here. So let's look and see what happens as we vary those. And we've got here, here's the exhaust valve opening. The exhaust valve opens near bottom dead center, but always before bottom dead center. And since the piston moves more slowly at bottom dead center, it's not unusual to begin opening some 60 degrees before bottom dead center. Once again, because of the inertial forces in the valve train, particularly if eventually we run the engine at a high RPM, we're going to end up having to begin opening it much before we'd like to have it completely open. What is the advantage of running the engine at high RPM? Well, the principal reason. Can I help you with something here?
Not at all.
I'll try not to help you in the future. You see here, as we vary the point at which the exhaust valve opens, and you can once again see the range in the crosshatch portion up the top, the spark advance doesn't change. Why would we expect it not to change? Here we're changing the point at which the exhaust valve opens over a rather wide range. The range goes all the way, it's like this. All of it, as you look at the crosshatch, is before bottom dead center. It's all in the normal range. And as we open it later or earlier, we still require the same spark advance. Why is that?
It doesn't matter, right? Because if you let it out,
It has no effect on residuals. It has no effect on the turbulence in the chamber. The gas is still going to enter at approximately the same speeds. So we haven't changed the flame speed, so we don't need to change the spark advance. But the exhaust gas temperature is slowly increasing as we open later. What's happening here? The range that we're operating on is like this. And at this point, when it's very early, the temp is lower, and here, temp is higher.
there's more time for heat losses if you open it later, right?
As we open here, the gas velocity as we enter the exhaust port, remember, the final exhaust gas temperature is a function of the heat we lose during the cycle and the heat we lose during the exhaust port. As the gases pass through the exhaust port at a lower velocity, they don't lose near as much heat. So they end up at a higher temperature even though they start out at a lower temperature. It's not a lot. You can see here, we're talking about maybe 30 degrees, but the temperature is going up because we're reducing the heat losses in the exhaust port faster than the temperature is dropping over this range of expansion.
Can you repeat that, please?
Yeah. The exhaust gases, before they leave the chamber, before we open the exhaust valve, as we go through this portion, the gases are dropping in temperature because we're taking some work out of them.
Yes.
But as they go to the exhaust port, they lose quite a bit of heat. When we first open the exhaust valve, we're going to be in a neighborhood of somewhere between 50 and 100 psi. So the gases are leaving the cylinder at the speed of sound. If we're at 100 psi, the first 3/4 of them leave at the speed of sound. If we're down to 50 psi, the first 60% leave at the speed of sound. But those gases have a very, very high heat transfer coefficient because they're moving comparative to the metal they're passing at a much higher rate than they would in the combustion chamber. So the heat loss into the exhaust port is quite large. And that just ends up in the water jacket, and at some point the radiator has to remove it, but that heat loss is the one that is reduced when you open the exhaust valve later, because we're in a lower pressure. And that's big enough so that the overall temperature of the exhaust gas climbs, not a lot, 30 degrees. Cylinder to cylinder, you can easily find a 30-degree temperature differential. This work was done with a single cylinder version of the 400 cubic inch displacement V8. So they got rid of that effect. But the exhaust temperature is actually going up, which is counter to what's happening to the gases in the cylinder. And an indication of the rather large amount of heat transfer that occurs into the exhaust port. And all that does is make it harder to run the turbocharger because you have less energy available. It makes it so that the radiator has to do a bigger job. It also means that a catalyst doesn't light off as quickly, and consequently the catalyst can't do as good a job in the very early portions of the cold start. Okay?
This still doesn't make sense to me that it goes up.
Yeah, I'm still trying to understand.
It's still
Well,
in the middle.
When I send the gases through the port at a higher velocity, what happens to the heat transfer coefficient?
Goes up.
Goes up. What happens to the heat losses in the exhaust port?
Goes up.
Goes up. So as we go through
But we start with a lower temperature, right?
we start at a lower temperature, but initially we're at a much higher velocity because we're at a higher pressure. We sustain that sonic flow for a greater length of time.
So
There's more time overall for the entire process because we started earlier, but we're sustaining the high velocity, those sonic velocities, for a greater length of time. And that's associated high heat loss in the exhaust port works counter to the temperature drop here. And it is larger than, over the range that they've chosen here for operation, it's larger, so we actually get this very small 30-degree increase in temperature in the exhaust gas temperature as we're opening the intake valve later and later. The rest of the cycle, we can see from the spark advance, is not changing appreciably. But there's two things that happen counter to one another to produce exhaust gas temperature. You have the heat loss in the combustion chamber and the heat loss in the exhaust. And the heat loss in the exhaust, even though the temperatures are lower, is very, very large because the gas velocity is so much higher. When the hottest gases leave initially, during that time, that's when they're passing the exhaust valve, exhaust seats, and the stem and
Because
everything.
they leave at a higher pressure.
Right.
Or
Here, they leave at a higher
They
pressure.
lose a lot of heat.
So yeah, they're going sonic for a much greater length of time, and here when they're going sonic, they're at a higher density.
Yeah.
So what happens to the heat transfer that increase in heat transfer is large enough so that it overcomes the temperature drop that we see very late in the expansion stroke. And the temperature drops are beginning to flatten out, of course.
So is the expansion of gases quicker when you open it up earlier as opposed to the expansion of the cylinder?
You mean are they leaving faster than they're being?
Like I'm saying, by opening it up early, are the gases expanding quicker that way than they would if they stayed in the cylinder?
Expanding out of the cylinder?
Yeah, because the gases are expanding when you open the.
Yeah. If they're at a higher pressure, they're gonna leave at a higher rate. They're still leaving at the speed of sound, but they're at a higher density when they're leaving at the speed of sound.
So is that rate of expansion quicker than they would be expanding if you kept the valve
Oh,
closed?
vastly.
Yes,
Yeah,
that's
yeah,
what I'm trying to
absolutely.
get
It's
at.
like
So
getting
that's
a leak.
basically where they.
It's the difference in between taking a balloon and squeezing it or putting a pin in it. Once you open the exhaust valve, you have a passageway out to a very low pressure environment. So yeah. Once you open the exhaust valve, it's like sticking a pin in a.
So it's like an air compressor and leaving it open at higher pressures, you get that. Cool air.
Any container, the higher the pressure for the same orifice, the higher the flow rate. It's just that if that container, if you've got air or nitrogen or any of the diatomic gases with a ratio of specific heat of about 1.4, because that's what determines the flow rate. If you're at a higher pressure, they're all reaching the speed of sound, but they're denser if you're at higher pressure. So if you're 10% higher pressure, the speed of sound, you got 10% greater mass flow rate at the same velocity. And once you're above a pressure ratio of 2, you've got sonic velocity. So if we have 30 psi in the cylinder, which we're going to have to drop a long time from the original pressure at the end of the expansion stroke to 30, it's still sonic. If we start out as we, at high load, we end up, particularly turbocharged engine, can end up way over 100 psi. But if you're at 100 psi, you lose about 3/4 of the gases out of the chamber without pushing them out with the piston.
So the pressure ratio is that exhaust divided by intake? The pressure ratio you just talked about?
Yes, yeah.
Okay.
The pressure ratio past the valve. And you've got the cylinder pressure on one side, and you've got the atmospheric or exhaust manifold pressure on the other. You can estimate that to be like 15 psi. At these light loads, it's going to be almost atmospheric. The pressure drop through the rest of the exhaust system at these 1200 RPM and 50 psi IMEP, perhaps 20, 25 psi BMEP, at these very, very light loads, is very, very small. Remember, the pressure drop goes with the square of the velocity. So if we cut down the velocity by an order of magnitude, we cut the pressure drop by 2 orders of magnitude. And a high pressure drop is still only PSIs. That depends on the catalyst and the muffler. Those are the two principal, and the catalyst being the larger pressure drop, but those are the two items in the exhaust system that cause an appreciable pressure drop. The piping itself is small, but pretty negligible compared to the others.
Is this sonic throttling? Or is that something else?
Pardon me?
Is that sonic throttling? Or is that something else?
Absolutely.
Absolutely.
That's absolutely. Does everybody know what sonic throttling is now? Well, let's go through it again. Do I need to?
Yes.
Okay. Let's see, I have 2 containers, and this is low pressure. Well, let's put a number on it. There's 15 psi initially, and here's 100 psi. The gases that go through here cannot go faster than the speed of sound. Once these gases reach the speed of sound, this tank doesn't know what the pressure here is anymore. I can lower this pressure down to 5 psi, and I've got exactly the same flow rate, exactly the same mass flow rate. We're going to run into this here where you deal with Mach index number later in this class. This is sonic. This is a basic phenomena of fluid dynamics. If we've got a pressure differential here, and it's very small, it's a laminar flow here, right? And then when I hit, if this is a round tube, when I hit Reynolds number 2000 or so, it goes turbulent. and we begin to build up eddies. When it's laminar, the velocity is linearly proportional to the pressure differential. If I double the pressure differential and it's still laminar, I get double the flow rate. But once it goes turbulent, and this is what gases always do, then the pressure drop is proportional to the velocity squared. It's exponential now, okay? So as I continue to go past sonic, I reach the point where if this is 30 psi, I drop the pressure to 15 psi. You know, I start up here, if this is 30 psi, I start up here at 30 psi. I get no flow at all, right?
Yeah.
I drop this down to 29 psi, and I have laminar flow through here. Depending on how thick this is, the thinner it is, the easier it is to get laminar flow because it's all in a laminar boundary layer. Remember the laminar boundary layer? So I get 29, it's still laminar. I get up here to 25 psi, I got 5 psi difference, that's huge. It's turbulent now, but it's not sonic. By the time I get down to 15 psi, these gases are moving at the speed of sound. Now, any pressure waves difference in a gaseous medium can only travel at the speed of sound, right? If I make a noise up here, you don't hear it the instant I make it. For those changes in pressure in the gases in the room, in the air, to reach you takes whatever distance it is divided by the speed of sound, okay? So, for this to know if this is at a lower pressure, that wave has to propagate back up here. This low pressure wave has to propagate back up here, and that's not possible. Because these gases are moving at the speed of sound, and this can only move at the speed of sound. So once I get below 15 psi, I can go to 10 psi, and I get exactly the same flow rate. Theoretically, there's slight differences due to inlet and outlet and stuff like that, but in a very theoretical sense, it's the same. 5 psi stays the same. That's sonic throttling. We have reached the point where the gases are moving at the speed of sound, and consequently, the high pressure side doesn't know what the low pressure side's doing anymore. There's no way for that low pressure information to pass at the speed of sound back upstream, or a stream that's moving at the speed of sound. This is the phenomena that stops the horsepower output if the engine doesn't brake of all engines. Because as you increase the RPM, you're dropping the average pressure in the cylinder. There is some restriction in between the atmosphere and the cylinder. You got an intake valve or 2 intake valves, an intake port, runner in the manifold, some throttle body, all those. So when I try to pull air through there, there's a pressure drop. And as I try to pull it faster and faster, it's a bigger pressure drop. When I'm trying to pull it to the point to where the average pressure is now half an atmosphere, I can't get any more in. And the torque starts to drop dramatically, because if I take the RPM higher to lower that pressure, I get an increase in the friction, but I got the same mass flow rate of fuel and air into the engine, so into the cylinder. So I can't make more torque.
So is that between the intake and the cylinder, not between the intake and the exhaust?
Yeah, this is between the intake and the cylinder, but it works for any pressure differential with any orifice. This is just fundamental fluid dynamics. This is the way gases behave. Okay? So what we're talking about now is the high pressure cylinder and the atmosphere, but in a few minutes we're going to be talking about the atmosphere and the cylinder on the intake stroke. And it's the same thing. We can't go faster the speed of sound in or out. Okay? We can use a supercharger and make it so the mixture is denser, so at the same speed of sound, now if we double the density, we got twice as much mixture in the cylinder, and all we want is to get a lot of fuel and air in the cylinder if we want to make more power. Specifically, make more torque. Power is torque times RPM. We like to go to high RPM so we can make a lot of horsepower. If an engine makes a lot of horsepower, we can use a little version of that engine and get extremely good mileage. Or we can give the customer what they end up typically wanting, same size and better acceleration. That's how in the world we got to the point where we have multiple vehicles today you can buy from a dealership at over 700 horsepower. It turned out that that's what we sell, and that's what they make. Okay?